So now we will start a new section, a new combinational circuit which is called multiplexer, or we will call this mux as short. So let's start from a 2 to 1 mux. So a multiplexer is a circuit that selects one of the inputs. So in this case we have two inputs, let's say I0 and I1, and I have a select signal here. I will call it S0, and my output is Z. So the mux will either select I0 and it will connect it to the output, either it will select I1 and it will connect it to the output. So two inputs are coming in parallel and I am only selecting one of them. Okay, so let's say this is our functionality table for this mux. If S0 is 0, I will be selecting my I0 and I will be connecting it to the outputs. If my S0 is 1, then I will be selecting I1 and then I will be going to the output. So either this goes to the output or this signal goes to the output, right? So I am selecting only one of my inputs. So if I can make a truth table for this, so this is my I1, I0 and my S0. So these are my inputs and this is my outputs. So this is my 8 possible inputs. If S0 is 0, I am selecting I0, right? So then this I0 goes to output. So Z will become 0. If S0 is 0, then I will be selecting this and then Z will become 1. If S0 is 0, I will be selecting I0 and this value will go to output. If S0 is 0, then I will be selecting this I01 and then this I0 value will go to the output. So if S0 is 1, then I will be selecting I1 and this value will go to the output. If S0 is 1, I will be selecting I1 and this will be going to the output, right? If S0 is 1, I will be selecting I1 and it will be go to the output. And if this is 1, I will be selecting I1 and this will be going to the out. So this is the truth table for this 2 to 1 mux. So how do I implement the inside circuitry of this 2 to 1 mux? So since I have my truth table, I can look at where the Z is 1. So I need to find out these conditions, right? Where the Z is 1, right? So how can I do this? Of course, I can always draw my Carnot map. So this is I1, I0, and this is S0. So in this case, I have a 1 here, another one here, another one here, and another. So I have 4 ones for my Z. Let's group them. So this is one group and this is another group. So this is represented by S0 not I0 and this is represented by S0 and I1. So my Z is given by S0 not I0 or S0 I1. So this is expected because if S0 is 0, right? If S0 is 0, then Z is equal to I0. If S0 is 1, then Z is equal to I1. Actually, this Boolean function is describing what is the functionality of our circuit. So after finding this, so what is inside this? We can draw the functionality here. Let's do it here. So what is inside? So I have I0 and I1 here. So I have S0 here. So this is I0 and S0 not, or I1 and S0. So I have an OR gate here and this is my Z output. So this is a 2 to 1 multiplexer. So let's do a real life example. So let's say I would like to implement something like this. I will be just write the pseudocode. So this means I'm just describing what I am trying to do. Like I will say if S is equal to 1, then I have a function f, a and b, else f is equal to a or b. Okay, so this is what I am trying to do. So how do I implement this in digital design? I implement this using a multiplexer, right? So this is doing if else is doing a multiplexing operation, right? So this is a basically doing a multiplexing operator. So how do I implement this? So this is a and b, and I have a, b, I have a an OR gate here, and I have a multiplexer here. So this is my S. So this is actually the other way. So this will be an OR gate and this will be an AND gate. So if S is 0, I am getting this, right? If S is 1, I will be getting the AND operation, and this will be my Z. So this is a real life example of where do we use this multiplexing operation. Okay, now let's start 4 to 1 multiplexer. So what we have seen in the previous case, 2 to 1 multiplexer, but we might need more inputs for the multiplexing operation. For example, if let's say I have a variable A is 1, let's say A is 0, then do this. Else if A is 1, do this. Else if, right, A is 2, then do this. And else, then do another thing. This is implementing a 4 to 1 mux, right? So let's see what is the inside of this multiplexer. It is very similar to 2 to 1 multiplexer. So in this case, I have 4 inputs, I0, I1, I2 and I3, and then I have 2 select lines. So this is S1, this is S0, so this is 4 to 1 mux, and I can say this is my out Z, right? So why do we have 2 select lines? Because we need to select one signal out of 4. That's why we need 2 select lines, right? So in 2 to 1 mux we had only 1 select line. So let's do the functionality table for this 4 to 1 mux. So I have this S1, S0, and I have this output C. So I have written all the possible input combinations for the select signal. So in this case I will have I0 for select signal 0, 0. If my select signal is 0, 1, I will be selecting I1. 1, 0, I will be selecting I2. 1, 1, I will be selecting I3. So one way of finding this circuit for this, we need to write the truth table, right? But this will be very long, right? Because we need to write 64 lines because we have 6 inputs to find out Z. Then we need to use the Karnaugh map to simplify it. But instead, I can directly write my Z function. How do I write this? If select signals S1 and S0, 0, 0, S1 not and S0 not, then I select I0. Or if my select line S1 is 0 and S0 is 1, then I select I1. Or if S1 is 1 and S0 is 0, then I select I2. Or if S1 is 1, S0 is 1, then I select I3, right? So this is my Boolean function for this 4 to 1 multiplexer, right? So as you see, we have 4 terms here, but only one of them is active at a time. So I am only selecting one term out of 4 terms, right? So, and these select signals are making sure I only select one term, right? You cannot select 2 terms at the same time because only one of these select signals outputs is 1, the others are 0. So if I would like to draw the circuit for this, I will be having 4 AND gates. And these AND gates will be ORed together because I will be selecting only one of them. So this will be my I0, this will be my I1, I2 and I3. So I will be selecting only one. So how do I make sure I am selecting one of them? So I will be having this select signal S0 not and S1 not here. So we have S0 directly, S0 is 1 and S1 is inverted. So for I2 I have S0 not and S1. For I3 I have S0 and S1 together. So this will be my Z. So this is a 4 to 1 mux. So the idea is the same as 2 to 1 mux, right? So this was the 4 to 1 mux. Okay, let's do an example. So let's say I would like to do an addition, the add operation. Okay, so I have some signal A. So this is a 4-bit variable. Okay, so this is a addition operation. Okay, this is not an OR. A plus B plus C plus D. So all of these variables, assume they are 4 bits, okay? And I would like to do this addition, but I have only one adder. So assume I have only one 4-bit adder. So how can I do this addition? So what I can do this addition one by one, okay? So let's say I have these A, B, C and D, and each signal is, these are again 4 bits, okay? With this line here, I am telling they are more than 1 bits, okay? These are 4 bits. So I have again some select signals here. So this will be my 4 to 1 mux. So first I will be selecting A, and let's say I have an adder here. This is a adder. This is a 4-bit adder. So you can think I can take this output and connect it to the input for adder. Let's say this is X and Y. So to the Y input of this adder, and I will be getting, let's say this is my Z, right? So initially I will make sure my S1, S0, 0, 0. My X is initially assume this is 0. Okay. And Z, this is my output. So initially is everything is 0. So what happens if this is 0, 0? I will be selecting. So this is my 0, 1, 2 and 3 input. So if this is 0, 0, right? Let me do this. So initially I don't define my S1 and S0. So if I make it 0, 0, then my X input will be A. Since initially Z is 0, so I will have 0 here and A here. If I add A and 0, I will get A here. So my Z will become A. Let's say after some time I change the select lines to 0, 1. Now I will be having this B to go to output. Now I will have B here. So instead of 0, now I will have A here. Now at the output I will have A plus B, right? The next time, so I will have A plus B in this case. So let's say after some time I change my select signals to 1, 0. So if this is 1, 0, then I am selecting C and I am connecting it to the output. So now my input is C here. So, and for the Y input I have A plus B here, right? Now at the output I will have A plus B plus C, right? So this will be C and I will have A plus B plus C. And after some time, now I will change my select signal to 1, 1. So I will have 1, 1 here. So this means I will be connecting D here. So the X input will be D in this case. And now we have A plus B plus C for the Y input. And we will have D here. And at the output I will have A plus B plus C plus D. Right? So by using this multiplexer and one 4-bit adder, I was able to do this addition A plus B plus C plus D in successively, right? One by one I did this addition. I only used one multiplexer. So this is one other application of this multiplexers, right? Sometimes we need to do some serial operations and we need to change our inputs. In that case we can use these multiplexers in our circuit. Of course this is just to show you the basic idea, right? We need to make sure if we do the addition there should not be any overflow. We need to make sure our operation is correct. But in this case we ignored this overflow operation just to show the functionality of this 4 to 1 mux. Now let's look at 8 to 1 mux. So in this case I will have 8 input I0, I1 and it will go down to I7. And I will have 3 select lines in this case S2, S1 and S0. So we can write the functionality table for this. So this will be my Z. So if this is 0, 0, 0, I will be selecting I0, 0, 0, 1. I will be selecting I1 and it will go down to 1, 1, 1 and I will be selecting I7 in this case, right? So, and then I can write the Z function. So it will be S2 not, S1 not, S0 not, I0 or S2 not, S1 not, S0, I1 or it will go to up to S2, S1, S0, I7, right? So if you want to implement this, we will again have 8 AND gates here and we will have a OR gate here and this will be our Z and this will be I0, this will be I1, I2, I7. So then I will be connecting this AND gates with the select signals, right? This is S2 not, S1 not and S0 not. So you get the idea, right? So you will be doing a similar approach for this 8 to 1 mux. Okay, now let's do another example. So we can build a larger muxes using smaller muxes. So in this case we are asked to build a 4 to 1 mux using 2 to 1 muxes. Okay, so I need to implement a 4 to 1 mux. So I will have these 4 inputs, let's say I0, I1, I2 and I3 and this is Z. and I will have this S1 and S0. But inside this, I need to use 2 to 1 muxes. So this is 1 2 to 1 mux. So this is another 2 to 1 mux, and this is another one. So this is 0 1. So this is S0. This is S1. Let's call them. Let's S1 S0. S0 0 1. Let's call them something else just to make sure these are different signals. Let's say this is select signals R1 R0 for the 4 to 1 mux. Okay, and these are my outputs. So given this, so how do I make the connections such that I will be having a 4 to 1 mux, right? So I will be connecting I0 here and I1 here, I2 here and I3 here. Okay, so this is 0, this is 1. And this output will be connected to here, and this will be connected to this one, and I will be having this connected to output. Let's do how to find out where to connect these R1 and R0. So let's say this is R1, this is R0, and this is my 0. So if they are 0 0, I will be having I0 here, 0 1 I1, 1 0 I2, 1 1 I2. So as you see from this table, right, if you look at here, R1 is either selecting the top one, or if R1 is 1 1, it is selecting one of I2 or I3. So in a way, R1 is controlling the upper part or the lower part. But nobody warned me, so these were 2 to 1 muxes. So I have only one select signal here, okay? So this was wrong. So this is only one signal. So this is S, this is S, this is S. So from this table, what you are seeing, this R1 is controlling either the upper one or the lower one, okay? That's why I need to connect R1 to the last multiplexer. And then if you look at the table, R0 is selecting either between I0 or I1, or it is selecting, like it is becoming 0 or 1 between I2 and I3. So if I need to make a selection between, I0 or I1, then I need to use R0, right? So I need to connect my R0 to this multiplexer, and if I need to make a selection between I2 and I3, I need to use R0 again. So this will be R0 again. So R0 is selecting between I0 and I1 or I2 and I3. Then this R1 is either selecting this group, one of this group or this group. That's why I need to connect R1 to the last multiplexer. Okay. So it is important for you to understand how to do these connections. So just look at this functionality table and then try to understand what is going on, right? So if you look at here, R1 is selecting upper or lower portion, just like this multiplexer, right? This multiplexer is selecting the upper one, this line, upper line, or the lower group. Okay, that's why I need to connect R1 to this select line. We can see if it is working correctly, right? Let's say R1 is 0, R0 is 0. So if this is 0 and this is 0, I have I0 here and I have I2 here. Now R1 is 0, so I have a 0 here. So I will be having Z will be equal to I0. Okay. So if you try other cases, you will see this circuit, these connections are working fine. So let's do just another case and then see it is working. So let's say in this case I select 1 and 0. So if R0 is 0, 0 0, then I have I0 here and I have I2 here again. But now R1 is 1, so I have a 1 here. Then this I2 goes to Z. So this Z will become I2 in this case if the R1 is 1, R0 is 0.